Hey guys, today's video is going to deal with the deviation from the ideal gas law behavior. Okay, first and foremost, it's important to realize that there is no such thing as an ideal gas. Okay, we make this assumption so we can use the ideal gas law, right? The PV equals nRT, in addition to Boyle's, Charles, Gay-Lussac's. That being said, this ideal gas behavior is explained by the kinetic molecular theory, which is a phenomenal theory. It holds up really, really well. However, there are two major components that aren't true for real gases. Okay, the first assumption that we make, in the kinetic molecular theory, is that the volume of a gas is really, really small compared to the volume of its container. Right, the gases are mostly empty space. The problem with this, of course, is that real gases do have volumes themselves. And depending on the conditions, this can create some problems, okay? The second thing is that, we're assuming, again, per the kinetic molecular theory here, that these gas molecules can be treated as independent particles. And that's not always the case that we're going to see here in a second. Very often these attractive forces, the intramolecular forces, they do exist, obviously. And for real gases, this again can create some problems that we're going to talk about as far as like clumping goes. Okay, so things don't always kind of act as independent particles, as it were. Okay, when it comes to these deviations, there's kind of two conditions that we really want to key in on. The first is that these deviations from ideality are going to become larger at really, really high pressure, okay? And then also at low temperatures. So it's best to study gases, if we're going to employ, some of these gas laws, at really, really low pressures and high temperatures. So again, at low pressure and high temperature, that's when gases behave the most ideally, and that allows us to use our, say, ideal gas law with the most certainty, okay? The way that we can kind of summarize this is that, bottom line, the closer a gas is to the liquid state, it's going to deviate from the ideal gas law more, okay? And we're actually going to take a look at gases in a little bit and just kind of evaluate them. And we're going to see, dependent on their intermolecular forces and their boiling points, which ones tend to behave most ideally. Okay, so let's start by taking a look at the effects of temperature. Okay, imagine that we are talking about an ideal gas, right? So this is going to be kind of at high temperatures. And just for simplicity's sake, we have 5 particles here. So they're all acting independently. Okay, we see that they're maybe colliding with each other, but they're also colliding, with the inside walls of their container. Versus at really low temperatures, okay, where things are not ideal. At really low temperatures, keep in mind that temperature is proportional to kinetic energy, okay? So if we have really low temperatures, that is to say that these gas molecules all of a sudden are moving very, very slow. And when their speeds are slow, this allows for the intermolecular forces to become significant, right? So hydrogen bonding, dipole-dipole, dispersion, this, takes 5 kind of effective particles, and now all of a sudden we only have 2, we'll just call it effective particles, okay? So we should expect that deviation will exist, right? With 2 effective particles, we're going to expect that there's going to be less collisions. And that's what pressure is defined as, right? It's the number and the force of collisions with the inside walls of whatever container the gas is confined in. And so if the frequency of collisions goes down, if we're talking about a rigid container, then this is going to manifest as a artificially low pressure, okay? If it's not a rigid container, we would normally get a lower pressure. And now, if inside of that container the pressure is lower as compared to atmospheric pressure, that atmospheric pressure acting as a force will actually reduce the volume until those 2 pressures become equal, inside and outside of the container, okay? So bottom line is, as far as temperature goes, we want to study gases when they are most ideal. So our models are kind of as accurate as possible. And that means that we're studying gases at a really high temperature to kind of eliminate largely the effects of intermolecular forces. Okay. Pushing on, let's take a look at the effects of pressure. Okay. When it comes to pressure, we're kind of talking about the same thing, at least initially. Okay, so at really high pressures, the observed volume is going to be less than predicted by the ideal gas law because of attractive forces, right? We have closer spatial distribution. So as a result, these particles start to clump. Again, the dipole forces, the hydrogen bonding, the dispersion, they're going to take, say 5 effective particles down to 2. Okay, so this is very similar at high pressures to what we see with low temperatures. And then things get a little weird, right? So at really, really high pressures, like insanely high pressures, the observed volume is actually higher. And this is a little tricky to kind of think about, but at this point, the spatial distribution is so close, right? It's so close that the gases are no longer mostly empty space, okay? And so now all of a sudden what we have to do is, we have to start thinking about the fact that these gases do have volume themselves, and this volume becomes so significant that it actually contributes to the overall volume, okay? Our textbook does a really nice job of kind of firming up the second point here, but again, take-home message is just that we want to study pressures at gases at really, really low pressures. Because at low pressures, we're going to minimize the effects of intermolecular forces, right? We're also going to limit the idea that gases have volumes themselves, okay? So let's take a look at the situation here. Imagine that we have the following 3 gases, right? So gas X, Y, and Z, and they all have these different boiling points. And recall that our boiling point is the temperature at which we're in equilibrium between the gaseous and the liquid state. So the question is, which gas will actually show the most deviation if, say, we're at room temperature and we just begin to drop the temperature, right? So we go from 25, say, to 20, 15, 10, so on and so forth. Well, the answer is that the gas that transitions from the gaseous to the liquid state first, that's the one that we should expect to see deviate from ideal conditions first, between these 3 gases. And so that's going to be the one with the highest boiling point, right? So this one is going to be the first gas we see, gas X here, that transitions from the liquid to the gaseous state, okay? And at negative 20 degrees Celsius, that's not that far off from room temperature. It's possible that straight away, we are already seeing gas X kind of deviate from ideal gas conditions. Okay, it's possible that PV equals nRT may need some corrective factors in our equation to account for volume and intermolecular forces. Okay, from there, as we continue to drop the temperature, we're eventually going to get gas Y to transition to the liquid state. This is going to be the second one that would begin to deviate from ideal conditions. And at negative 220 there, we're pretty far off, obviously, from room temperature. These two are going to remain ideal for quite some time. And so the idea is that when we're studying these and we're taking a look at those relationships between volume, pressure, and temperature, we should expect that our mathematical models hold true for quite some time. All right, thanks, guys.